Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. On today's show we'll discuss antiderivatives and integrals. Antiderivatives are just the reverse of taking derivatives. It's going backwards. Given a function f, we ask what function has f as its derivative. And we have a definition. A function capital F is called an antiderivative of f on an interval I if capital F prime of x is equal to little f of x for all x in I. What does that mean? That means big F is a function whose derivative is little f. If we start with little f, we want to find a big F that has little f as its derivative. Here's a key result. If big F is an antiderivative of little f, then the most general antiderivative of little f is big F of x plus c. The key point is that we've already shown that if two functions have the same derivative on an interval, then the functions can differ by only a constant. So, therefore, if we know one antiderivative of little f, any other antiderivative of little f on an interval has to be the same up to a constant. Why is that? Well, if I take the derivative of big F plus a constant, I'll get big F prime plus 0. So that constant won't change the derivative. And that's the only thing that won't change the derivative. How do we find the antiderivative? Well, we have to think of what type of function has a function of the form given as its derivative. So if we know the derivative, where does it come from? This thinking is different than for taking derivatives. There's no set formula like the limit definition of a derivative formula for doing an integral or for doing an antiderivative, which we'll find out later on is doing an integral. So, for example, if we have f prime of x, the antiderivative of that, where does that come from? That comes from f of x. Think of each of these other functions and think of what function do you know which has these functions as the derivative, right? E to the x, the derivative of what is equal to e to the x? The derivative of what function is equal to secant squared of x? The derivative of what function is equal to 1 over 1 plus x squared? And here are the answers, right? The derivative of little f is little f prime. Derivative of e to the x is e to the x. The derivative of tan x is secant squared x. The derivative of arc tan x is 1 over 1 plus x squared. Really on the right, we could add a constant to any of these functions and the derivative will not change. Some of the applications of antiderivatives are that the antiderivative of acceleration plus possibly an initial velocity, gives the velocity at any instant. Since the derivative of velocity is acceleration, the antiderivative of acceleration is velocity. Similarly, the antiderivative of velocity gives you the position when it's adjusted for some initial position. Another application of antiderivatives is in finding the trajectory of a projectile moving under the influence of gravity. And you've probably learned about that in your physics classes. Now let's go on to integrals. We can approximate the area under a curve by considering rectangles and taking limits as the width of these rectangles go to 0. Let's take a look. We have the function y equals x squared, and we're presenting it on the interval from 0 to 1. And we consider what we call left rectangles, where we consider the left point of an interval. Here, the interval from 0 to 1 is broken up into 4 pieces. Each has width 1/4. And we make a rectangle under the curve at x equals 0, at x equals 1/4, at x equals 1/2, and at x equals 3/4. And we can see, at least for the curve y equals x squared, the area under these rectangles give an underestimate of the area under the curve. We are missing these pretty triangular shaped portions. On the other hand, if we consider right rectangles, that is a rectangle with the y value at x equal 1/4, at x equal 1/2, at x equal 3/4, and at x equal 1, we have an overestimate. We have these upper rectangles, which is going to give us an overestimate of the area under the curve. We could add up these areas for the left rectangles. We find the area under the curve the sum of the areas under these rectangles is 0.21875, and under the right rectangles it's 0.46875. And for the case at hand, we can approximate that the true area under the curve is somewhere around the average of these values. Okay, an application of finding the area under the curve is in approximating the distance traveled when a velocity is given at several times. As we noted earlier, that the position is given by the antiderivative of the velocity. Another way to look at that is to consider the velocity as rectangles and consider how long one is traveling at each velocity. So suppose we're going at 25 feet per second, and then at 31 feet per second after 5 seconds, and then 38 feet per second after 10 seconds. We can approximate over 15 seconds what the total distance covered is. And we can approximate as the velocity 25 feet per second for the first 5 seconds, 31 feet per second for the second 5 seconds, and 38 feet per second for the third 5 seconds. This is the equivalent of dealing with the left rectangles. We add those together and we get an approximation that we've traveled 470 feet. Let's take a moment for math culture. There was a somewhat advanced society that had figured out how to package basic knowledge in pill form. A student, in the need of some learning, goes to the pharmacy and asks what kind of knowledge pills are available. The pharmacist says, "Here's a pill for English literature." So the student takes the pill, swallows it, and has a great new knowledge about English literature, can recite Shakespeare by heart. "What else do you have?" asks the student. "Well, I have pills for art history, biology, and world history," replies the pharmacist. The student asks for these and swallows them and has a new knowledge of all these disciplines. Then the student asks, "Do you have a pill for math?" The pharmacist says, "Wait a minute," and goes into the storeroom and brings back a huge pill. He's got a wheel in the pill, it's so large. And finally, he drags it in and plunks it onto the counter. "I have to take a huge pill like that in order to learn math?" inquires the student. The pharmacist replies, "Well, you always knew that math was a little hard to follow." Thank you for joining us today. Have a great day, and may the power of math be with you.